files, whatever it is, but whoops, let's get rid of that. So that's the web link to the PDF. I'll show it again at the end, basically, but I don't want to sort of prolong it because we've got a fair amount of material to get through, and I want to keep to the half hour so that we've got plenty of time for questions in this sense. So what I'm going to talk about, I've called this new urban science or city science, etc. But of course, the first point is there's not one science for the city. There are many sciences. The kind of science that I'll be talking about, complexity theory and scaling and so on, really is relatively new. It's not new within physics, basically, but it's relatively new within our particular domain, and it's very relevant to complexity theory. There's a number of issues, definitional issues, that really pertain to any science when it comes to be applied. And of course, in our context, we're applying these ideas to the city. And of course, in some senses, the city is a very nebulous concept. It's very ambiguous in a sense. I want to say a little bit about this ambiguity because it throws up this notion of whether we should look at the city as a physical object or whether we should look at it as a social system. And of course, we can't really say one or the other. It's in fact all of these different perspectives really in that sense. So what is the city is an important issue. Then I want to look at some of the history of this stuff, that if we dig back certainly to the middle of the last century, then we find regional science, which really comes out of urban economics and regional economics. We find the systems approach, which is complementary and to some extent but also opposite to complexity. Complexity grew out of the systems approach. And also in the middle of the last century, a whole variety of different operational models, computer models were built on the basis of regional science and location theory and indeed the systems approach. So I'll say a little bit about that, which is historical. And that leads me to talk about complexity and morphology, really, in a sense, which I suppose is the main thing that the main issue in terms of what material I'll be putting over here. That leads me on to talk a little bit about this new science, which is statistical physics. I'll introduce very briefly ideas about scaling, how things change with scale. And then I'll also introduce, almost as a digression, but it's very relevant to thinking about the broader context of how we can look at cities systematically and scientifically, the idea of the smart city. And I want to make a distinction between the high frequency city and the low frequency city. Most of what we've looked at over the last 100 years in terms of cities is the low frequency city. Now, by low frequency, I mean how cities change over years and decades and perhaps even over centuries. Most of our work in urban studies is really about the low frequency city. It's only since computers have come to be embedded within cities, and that's only happened within the last 20 years. And of course, the best example of that is all of us walking around in cities with our iPhones, incessantly streaming data in this particular context. So in some senses, the high frequency city, what's happening over the next few minutes, the next few seconds, the next few minutes and so on, is really a kind of another dimension to the city. It's not that people never thought about the high frequency city before we had computers embedded into the city itself and into ourselves really in this sense. It's basically that the computation which is spread out into the city has really given us the possibility to think about developing new ways of looking at what's happening basically through real-time streaming and through big data and so on and so forth. Okay, so that really is basically what I'm going to do. Now, I've made all of these points already, that what we're calling the new science of cities is not one science, but there are many sciences, but the new science of cities in this context is that really relates to complexity theory, which will become evident really, and also to some extent to big data. And this science is being developed really in analogy to the development of the physical sciences. Indeed, a good deal of what we know about cities is physical in some senses, but it has a slight nod to the social sciences. So it's back to this point I was making, the physical and the social sciences combine in this sense. There are other sciences too, of course, if we want to take as comprehensive a view as possible out of city, other sciences relating to, manufacturing, construction, and so on, to cognition, behavior, etc. A whole variety of different ways of looking at the city, almost as many ways of looking at the city as we have people thinking about the city in that sense. And that really, says it all. We're talking about complex systems, extensive systems. And the other feature, of course, is that we are moving very rapidly, I think, in a global context, from a world where we thought that we could make firm predictions to a world where the only thing that is predictable is the fact that it's unpredictable. The pandemic was perhaps predictable. It wasn't unexpected in a way, although the precise timing was perhaps unpredictable, always would be in this particular context. But there are many, many unpredictable things that really relate to the future. And if you look at our forecasts over the last 50 years or so of what's likely to have happened, both in the economy, in terms of cities and so on, all of them are wrong, basically. All our models are wrong, but some are useful, really. All our forecasts are wrong, but some are useful. I'll come back to that in a moment. Okay, if we go back to the beginnings of all of this sort of stuff, you can dig back almost indefinitely, certainly to the Renaissance. If you look at the works of Leonardo da Vinci, in particular, then you'll find that he talked a lot about motion. He didn't quite talk about gravitation. In a sense, that was left to Newton a few years later. But he talked about motion, basically. And of course, that really goes back to Greek philosophy as well, in that sense. So some of these ideas that we're talking about do go back a long way in terms of lots of different researchers and intellectual leaders thinking about them in this particular context. Here are some pictures from the 19th century, and I'll go through these very quickly, but they give you an indication of the focus of what we're talking about in terms of cities and complexity. Most of what we're talking about in terms of cities and complexity, the way we articulate them is in terms of dividing our cities up into locations, zones, if you like, in this context, and looking at the interactions or the flows between them. So the best example, of course, is classically a graph, basically, where you have a bunch of nodes and a bunch of links, basically, in some sense. And on the links, you have a dynamics, you have flows which actually move between different locations. And all of these examples, for example, we have von Thunen in the top left-hand corner. I'll come back to him because he's really the architect of the way we think about the city economically today. There's a nice map there from France, basically, from Charles Minet, I think his name was, who had lots of interesting flow maps. That's Napoleon's march on Moscow, basically, and the thickness of the line really relates to the flow into Russia and then back again, and the decline of the army. And then we've got a picture in the middle there of the flows of traffic in Dublin in about 1830, basically produced by the British Army. The British government were intent on building a railway, basically. This was the beginning of railway building, and they did a survey in a sense. And then there are pictures of migration. This is Ravenstein's work on migration from the 1881 census in Britain, basically. So lots of forerunners with respect to locations and interactions in that sense. So that really establishes the focus. Let me say something very briefly about what is a city. One of the kind of key things in this whole question of complexity in cities and the systems approach is defining the objects with respect to the environment. Cities exist now in a global world, and it's increasingly difficult to define their boundaries in this particular context. And there was a famous paper in 1937 by Lewis Mumford. Lewis Mumford is really one of the, I suppose, one would call him an urban historian, really, in a sense. Wrote many books. The City in History was his last book in '63. But he wrote a paper in 1937 saying, what is a city? And basically in that paper, I've written an editorial on this, basically, but let me just pick a bit out of his paper. He argued that cities should be primarily considered as social institutions rather than physical artifacts. Everything about a city, he argued, such as its size and organization, its economic activities, can only be understood as part of its social functioning in that sense. So that's really a kind of a caveat, a warning, really, in some sense. the notion that defining a city is really all important. So everything that we do is relative to this question of how we draw the boundary around the city and whether the boundary is a physical one or whether indeed it's a conceptual one or a technological one, a virtual one in some particular context. So Mumford even anticipated ideas about electronic communications that changed the role of distance. Okay, so that's really the preamble. How are we doing? Sort of, I should really speed up, basically. Now, in the middle of the 20th century, I should say, there were a number of things that came onto the agenda. First of all, was the idea of the systems approach. We'll come to that in a moment. Basically, in a sense, and out of this, at the same time, came the idea of social physics, the idea of all this physics that was developed by Newton from the 18th and Leibniz from the 18th century onwards. Basically, a lot of that was thought about in terms of how we might not only deal with physical systems but also social systems. For example, gravitation is really quite central to a lot of thinking about how things located to one another in that sense. And out of this, in the middle of the 20th century, came this idea of urban economics and regional science. Now, these are the kind of key people, and I just want to emphasize very quickly what regional science and location theory and urban economics is all about. This is really applying ideas from mainstream economics to ideas about cities, in a sense. And von Thunen, who is our beginner at this in the early 19th century, basically produced the model, if you like, which is quite widely used at the present time in terms of urban economics. Alonso, who's the gentleman in the middle of that, basically, was at the University of Pennsylvania, wrote his PhD, and then his famous book, Location and Land Use, which really sketches the modern version of the von Thunen model, basically. And then there is Izard, who generalized a lot of this to what's loosely called regional science. So there they are again. Now, much of this analysis was based on systems, the idea of a systems, and this led to this notion at the same time of the systems approach, basically. And the systems approach really began to think the system as being an organized or manufactured system, more or less built from hierarchies of subsystems. And you can see that in terms of cities, how we divide cities into different sizes of shopping centers, different sizes of roads, hierarchies, basically, in that sense. And this was really the dominant paradigm in the middle of the 20th century. It conceived of the cities as being in equilibrium, basically, that if you disturb the city, it would move back towards the equilibrium and so on. And these were the kind of things that occurred. A lot of modeling really began with early computers in this sense. So cities were thought about really like machines, and we could build them as though they're in equilibrium. Now, of course, we know that all of this is very naive in many senses, that the whole point about complexity theory is that we're talking about systems which are in disequilibrium, or we should say far from equilibrium in this particular context. Let me move on. So out of all of this came operational models for urban planning, really, in the 1960s. And some of those models are still going. They're based on the notion of looking at interactions between locations and the flows. Basically, the typical model would be to take, for example, the dominant flows of traffic in the city, which might be the journey to work. In fact, it's no longer really the journey to work, but to take those dominant flows and to actually model them using ideas from gravitation to some extent and early mechanics, basically, in that sense, and to build operational models around. The first operational models were built in practice in the 1960s and have continued ever since. So let me give you an idea of what some of those models are like. These are all taken from our own work, basically, in a sense. So there's a book, Urban Modeling, Cambridge University Press, in when I was a young man, basically in 1976. And then there are some pictures of movements and flows. I'm not going to go into them in any detail. We're still working with these sorts of models. There's a strong and rich tradition of them. And you can see that they relate to locations and interactions. We've generalized it. We have a model that works for for England, Scotland, and Wales, I should say, largely, and it's web-based, it's interactive. You can run it. You can even run it on your phone, basically, in that sense, and it's very, very fast. It's optimized to produce results for flows in Britain in 30 seconds or so. Anyway, and those are the sort of pictures typically of that. And there is a paper in Urban Studies last year written by myself and Richard Milton called A New Framework for Large-Scale Urban Modelling. And that's really that tradition. There are other models, agent-based models and cellular models and so on, microsimulation models that are part of this broader tradition, basically. But this is an important benchmark, that these sorts of models really articulate a lot of urban economics and regional science, put them all together and build them into a context where we can think about using them, not to predict, because I've already said it's impossible to predict, but to actually explore the future in this particular context. Okay, now all of this stuff happened in the mid-20th century and onwards, basically, and really there was a lot of dissatisfaction with these models, largely because they assumed everything was in equilibrium. And the reason why that assumption was made was largely because the kind of data that we got access to was not temporally very specific. If you look at the cities that you're involved in at the moment, the easiest data to get is census data at a cross-section in time. We're beginning to get dynamic data over time from things like telephone calls and so on, but generally speaking, the dynamics was very crude in the sense that we're talking about different equilibriums over a period of, say, our censuses in most Western countries are every 10 years in that sense. So the 10-year change. And of course, everything can change within 10 years. So this notion of thinking about equilibrium was really quite problematic. Also, the idea of the city system as being conceived from the top down as a machine was really to some extent passé too, that really cities grow from the bottom up. If we look at them, most things in cities are not planned from the top down. They actually evolve from the bottom up in that sense. They're more like biological systems. They're more like animals than they are like machines. They're more like ourselves in that sense. And so the dominant paradigm began to shift. And this was embraced by complexity theory, really from mechanics, I suppose, to biology. That's a massive oversimplification to some extent. But really sort of organic thinking came onto the agenda rather than machine thinking in that context. And this really led to complexity, the idea that systems grew from the bottom up, they evolved, evolution was the watchword and so on. And some of the earliest statements of complexity theory were actually made in the 1960s. And let me just go through Warren Weaver, who was, if you ever looked at information theory, Shannon Weaver is a famous book summarizing information theory after the war, after the mid-20th century war, World War II. And Weaver basically, in his valediction address at the Rockefeller Foundation, where he was the director, talked about complexity. There's a paper in 1948, I think, called Science and Complexity. And he talked about simplicity, models of simple systems, models of disorganized complexity, and models of organized complexity. And it's organized complexity, biological and human systems, that really are the focus. They're by far the most complex. And Jane Jacobs, who wrote a famous book in 1961 called The Death and Life of Great American Cities, in her last chapter, she says that the way we should look at cities is using Weaver's ideas about complexity in this sense. Here are the pictures. These are very good and quite inspiring things to look at. Science and Complexity, you can get that if you just key into Google on the web. The Architecture of Complexity by Herbert Simon and his Sciences of the Artificial book too are really excellent, very readable and incisive things. And then the work of Christopher Alexander, but there's wrote a famous paper about city is not a tree. In fact, it's more complex than a tree. It's a lattice, basically. And there's a sort of little monograph on that that Mike Mahaffey organized. And then the early copy of, as you can see, a Pelican book. What's that? I can barely read it myself. 2 and 6pence, 6 and 6pence in the old money in Britain. So that really was from the 1960s. So that's Jane Jacobs' book. Now, all of this is very good background for this complexity. Let me summarize very quickly because I want to move on, and we'll probably skip some of this. Basically, you can look at it afterwards. As I'm conscious of time, I probably need 5 or 7 more minutes, basically, Hubert, in this sense. Okay, so in some senses, complexity theory is based on the notion that the world is so complex that it's impossible to make firm and definitive predictions. So unpredictability is the watchword of complexity, but also not unpredictability that you can just say, oh, it's unpredictable, basically, but unpredictability that enables us to explore the extent to which the world is likely to be stable or non-volatile in the future. The idea of a closed system or an open system is all important. The idea of feedback, positive feedback rather than negative feedback, these are all things that actually grow the system through time and enable us to actually begin to innovate. So it's about innovation, surprise, and things of that sort, technological inventions and so on. All of these things are quite consistent with the complexity view, where, for example, you're getting change, which is really a function of positive feedback in a sense, rather than, you know, at the moment we talk about the new normal, or in terms of cities, in terms of impact of the pandemic, the return to the old normal, the return to equilibrium. The pandemic, that's a classic example of packing. That's but basically the quickly actions, those still feature in the complexity approach. The idea that the world is becoming a 10 million, basically, in that sense. So that's given me a hint about the recording there that I'm coming to an end. Other notions about complexity can be of how we actually change the linkage and change the interactions as the system actually grows. Ideas about scale, agglomeration, and so on are all tied in with this in a sense. Now, here are some sort of complex systems. Now, nobody would ever, I'm not going to tell you where these are, but you can sort of guess. You can see London there, and then the southeast, etc. You can see Europe and so on. But basically, these are notions about complex systems. Grow up, they're self-similar, they scale, the same sorts of patterns repeat themselves, and nobody planned it, basically. It happens, you know, naturally, in that sense of ideas on fractal geometries and morphologies in this particular context. Okay, let me move on very quickly. Now, I'm not going to talk really in any sense about this. I just want to give you a pointer to the fact there's a variety of relatively simple models that take, for example, population, and they say, what happens if populations grow in cities? We certainly get an increasing number of interactions. If the number of interactions is p squared with the population, as I said a moment ago, 1 million squared basically for 1 million people in a city, and a number of possible interactions. Of course, the number of possible interactions will be much lower than the actual interactions will be much lower, much lower basically. But nevertheless, as cities grow, you get more opportunities. You get p squared in this particular context. And that to some extent is scaling basically. And there is a relationship, allometric relationship in biology that says that, you know, as the it's more than proportionately richer or more than proportionately poorer. That's allometry, basically, in that sense. And there are many relations of that kind. The gravitational relationship can be thought of as the same, putting together these two size effects for origins and destinations and so on. And that's very typical of the gravitational relationship used to look at flow between models, and these are other pictures. There's a third scaling relationship that really relates to city size, called a rank size, basically, Zipf's law in a sense. So all of these sort of things, and I don't have time to go into them, but they're all collected together, and they really form the essence, if you like, of complexity theory in this context. Now, how are we doing? I think it's 4 or 5 minutes more, because I actually just to introduce you to a little bit about the high frequency smart cities, the high frequency city, and big data. Now, so far we've really talked mainly about the low frequency city, although the low frequency city sort of merges into the high frequency, or rather the high frequency city merges into the low frequency if we get data which is produced in high frequency over a sufficiently long period of time. For example, in London, we have now 20 years of smart card data on the London transport system, and to some extent our short-term data, which is from our swipe cards or credit cards and so on, the Oyster card. The short-term data turns into the long-term data if we get long enough. So we can begin to see patterns at all scales, all temporal scales in that sense, as well as spatial scales in that sense. So to some extent, a lot of the development of the high frequency city is really to do with looking at patterns of interaction and location, but over a very short term. And this introduces a degree of volatility into our thinking about cities. It's very much far from equilibrium. There are many sorts of equilibrium, nested equilibriums, if you like, in this particular context. So here's an example very quickly of the kind of thing that goes on in terms of the high frequency city, the smart city. That's actually rail networks. Basically, it's very unfamiliar to you, I think, because we put them all on one, and embedded in that somewhere is the classic tube map, basically. Here, for example, is typically, is this started? Yeah, okay. So what you're seeing here is some synthetic data from the Oyster card database. And you can see origins, destinations, flows. I'll just talk over it. That's the Tuesday morning peak, and then the evening peak, and then a little peak at the end of the day. Whoops, black there. Then now Wednesday, basically, the morning peak, and then the evening peak. And then, of course, all of this data is, although there are patterns in it, they're patterns at all scales, basically. And here are pictures of the kind of thing that we get from that data. We've also got supply data in this particular context. You can see the bottom right-hand corner is the supply of trains. The top picture is the supply of passengers, basically. So we're interested in how we link passengers to trains, and that's a non-trivial issue. They're not synchronized, by the way, in a sense, but this is giving you an idea of the kind of data. It's big data because it goes on, and it's second by second in this sense. So here's typically. And if you think any of this is new, here's a picture back in 1939 of ladies in London transport actually counting tickets, origins, and destinations, even before computers were actually invented. And then there's a picture of pricing freight using early computers just after the Second World War in that sense. Okay, let me round it off a bit, and then we've got time, I think. So let me just say that clearly what I've not talked about is how we begin to fashion all of this sort of thinking and to mobilize it so that we can think about how we can invent and plan better cities. And I could talk a lot about this, basically, almost an entire session on just talking about fiction, really, in terms of how we use these things. And to some extent, the critical issue is predictability in all of this. In that particular context. And I said at the beginning of the talk, we live in this area of predictable unpredictability in this particular context. So the reason is, if we can't use these models to predict, and that's a much bigger question, and of course that's a very sort of blunt way of saying it. There are elements of the models that enable us to think about predictions over different periods of time, etc. But in general, it's not possible to predict the future in this sense. How do we actually begin to use them? And the answer must lie in exploration. It must lie in many models, more than one model of the same thing, because all models are wrong, but some are useful, as George Bock said. So there are many models of the same thing that we need to think about, and we can do that now. I mean, 50 years ago, when computers were as they were then, almost painful to just build one model, but now we can build many models, basically, in that sense. So we can actually begin to pit our models against each other and to actually develop different explorations of the future in this sense. So the critical issue is that these models will enable us to stretch our imaginations in that sense. And that means we need to think about a broader context of how we begin to plan using those models. Now, I'm going to stop at that particular point. There's a few more points here. Thank you very much. I did say that I'd give you an indication of some of the books that we've done on this. There's a very interesting book, an edited book that we put together, which is downloadable. That's the Urban Informatics book. There's lots of chapters in that on different aspects of urban informatics. And you can just, if you key it into Google, it'll come up and you can download the book basically. It's open access. And then there's a couple of other books that I've written, The New Science of Cities and Inventing Future Cities, MIT Press. And if you key those in, you might get the Chinese version online, but I'm not sure you're going to get the English version online. I don't even have English versions of the stuff myself in PDFs, but the Chinese are past masters of translating them, putting them online, basically. Okay, Hubert, that's it. I think we've got a little bit of time for questions, according to my clock, anyway.
Yeah, that's perfect. Really, thanks a lot, Mike, for this. Oh, do you hear me? Yeah, okay.
Yes, I can hear you.
Thanks a lot for this super interesting, fascinating lecture, as always. So now let's have our Q&A session. Well, if you have a question or several questions, actually, you would like to ask, feel free to raise your hand. Tabea, I see that you already have a question, so yes, please go ahead.
Yeah, so first of all, thanks a lot for this extremely interesting lecture. I have to say that your book, The New Science of City, kind of influenced me to become an urban scientist myself during the master degree. And it really had a strong influence on my understanding of urban modeling and urban complexity. And now I'm doing a PhD in spatial agent-based modeling of basically urban exposure, and also how basically interventions, trying to predict indeed how interventions change health behavior and exposure to air pollution and noise. It's a bit sad for me to hear that you say we're not able to predict the future, but so basically I have two questions also related to that, because I would be like really interested to hear in your words what exactly the added value is to model on the individual level, like the behavior on the individual level versus modeling on the population or system level, because human behavior is extremely difficult to model. It's I have that challenge, and I also feel like I probably cannot predict the individual, but I can aggregate it and analyze it on the system. I can go to the individual to have the exposure interaction and then aggregate on the system level. But I'm really curious to hear from you also what this added value is of course it's very relevant for agent-based modeling, but then I have a second question, if that's okay, and that is you actually ended the talk a little bit on that topic, that this like complexity and modeling insights, they have a clear use case for policymakers, right? So via simulations and predictions, and there's tremendous value, for example, using this to adapt and tackle climate change problems and predict effects of disasters or interventions. So I'm just wondering, I think we need, for example, more like modular collaboratory participatory modeling platforms, for example, where we can actually join our insight, because there's a lot of specialists as segregated. We need better data, but I'm really curious to see what you, for example, think is particularly missing for us to actually make use of this insight more for city planners and for actually having an impact on the planning of cities.
Sure. Okay. So let me address the first one. To some extent, we've been quite good at identifying different sorts of approaches to different sorts of models, really, at different scales and through different philosophies of aggregated versus deaggregated in a sense. But we've not been good at linking them. So in other words, aggregate modeling, for example, assumes that there are certain patterns and trends that are relatively stable, and we can use those to actually model in some sense and to predict. And agent-based models, of course, basically take a much finer view in a sense. And the reasons for aggregate versus disaggregate is that some of the things at the aggregate level that might be picked up can't be picked up at the disaggregate level, and vice versa, in a sense. That agent-based modeling is very suggestive because it enables us to begin to think about human behavior in a much more obvious sense, questions of cognition and so on. So if you look at pedestrian models, then you can look at how individuals interact with one another. To some extent, interaction is still basic to both aggregative and disaggregative in that sense. But agent-based models are much closer to our own experiences in some sense, whereas aggregate models tend to assume that there are patterns of statistical regularities, really, that we may or may not be able to explain very well. It so happens that in many of the aggregate models, the basic behavioral sort of structure really relates to how we view cost and distance in space, basically gravitational models classically in that sense. So to some extent, your point really was, how do we link, as it were, how do we walk across this spectrum from aggregative to disaggregative? And I don't think we know, basically. It's almost schizophrenic view of the world that aggregate modelers can also be disaggregate modelers and not be able to read them particularly across this spectrum, really, in that sense. It's almost as though there are different perspectives on the world which are very difficult to connect to one another, basically. And of course, if we broaden that to urban studies generally, there are lots of views about how people behave in cities that cannot be treated as agent-based models or aggregative models, etc., that have to be treated descriptively, that represent other perspectives, really, in that sense. So that's not a very satisfactory answer, but it sort of says that agent-based modeling is picking up things that aggregate modeling doesn't, and vice versa. And of course, it's a movable feast, because as we learn more about these different things, then those different aspects will in fact differ. So that would be my first response, I think, to what is a very big question, really, in that sense. Now, the second issue, I think to some extent, it relates to the idea that we might use many different models to handle policy questions to some extent. Many different types of models basically might be used in a kind of coordinated or collaborative way. When people began to think, well, maybe there's more than one model that is necessary, more than one model of the same thing to look at certain policies. Of course, this began in the 1950s and 60s, I think, in terms of the sort of military at the places like the Rand Corporation and so on in the Cold War, basically. But it moved very quickly, this notion about building more than one model, into the kind of models of the economy. So the Federal Reserve and the Bank of England and so on have a portfolio of models, econometric models, that predict the economy over different time periods, over the short term, the slightly longer term. And they have like a handful of models. I mean, I think, I don't know chapter and verse on this, but we're talking here about a dozen models, perhaps. A dozen econometric models are being run at any one point in time to make predictions about the British economy. They're all slightly different, okay? And of course, the essence is, how slightly different are they, basically, in some sense? And that's where the comparability would come in. So in some senses, this is the notion that we need more than one model to handle any kind of policy problem, really, in this particular context. And I concur with this in some senses, although again, it's a movable feast, because we don't have an awful lot of experience of thinking out of the box on this one, in terms of thinking about how we might begin to plug different models together. We have this model called the quant model, which is the one I showed very briefly for the UK, or England, Scotland and Wales, basically. And that model is linked to something called the Spencer model, which is a microsimulation model of the UK demography. That's built by a team at Leeds, basically, at Leeds Geography, basically. But the two models, our model and the Leeds model, are coordinated through the through a project at the Alan Turing Institute. And in other words, here are two models developed quite separately on different aspects of the UK economy, and we're plugging them together in that sense. And it seems to me that that's where we need to try and make some progress. We can't go too far on that because often plugging two or more models together leads to inconsistencies. My own personal preference is to try and build, you know, a completely consistent model from scratch over all these sectors. It's not able to do it. There's just too much detail and constraints really to be able to do that. So I think that was your sort of second question really. And I suppose complexity theory justifies in some sense, or at least legitimates, this idea of more than one model. I'll stop at that point.
Thanks a lot. I think I need to give time to the others to ask more questions. Thanks a lot.
Yuki, yes, you have a question?
Yeah. Hi, Professor. Thank you so much for your presentation. I'm Yuki. I'm a grad student at NYU CUSP and a research assistant at the GovLab. And I actually attended your seminar on digital twins a while back at CUSP research seminar. And I was wondering what you think is the role of open data and data collaboratives in the development of digital twins, and then what kind of open data and data sharing do you think is necessary for the future? It could be from like private telecommunication company opening up their data to researchers. I really appreciate if you have any like case studies or literature on the intersection of open data / data collaboratives and digital twins.
Well, I think we need to do two things in relation to unpacking your question. I mean, one is the whole nature of what is a digital twin. And to some extent, a digital twin, and then to go back one stage even further, then say, is a digital twin a model, right? In this particular context. And of course, it is a model in a sense, but it's a model with a difference. My view is increasingly that a digital twin is a model of a system that is very close. And of course, here begs the question, very close to them, basically. So an excellent example of this would be a building that had been built, a BIM model, basically, a building information model, a model that is used to actually help design the building, that almost then becomes part of the building itself for its maintenance and its continued operation, basically. And you can see how this is the case. You know, if you look at how buildings are controlled these days using sort of, they're using models basically that are contained within the structure of the building, but those same models might have been used to help in terms of designing the building and to redesign the building through time. So in other words, a digital twin is as close as possible to the real thing without being the real thing, of course, in this particular context. And to some extent, if you have different data sets of the same system, then these can be thought of as being digital twins. Rather than digital twins being models, you can think of them as perhaps being data in some senses. So, and I don't think much work has been done on this, but if you take telephone data, for example, there are lots of different, well, I guess different operators who are collecting this data from different types of calls and so on. And in some sense, these are twins of each other, basically. They're trying to collect the same thing. Actually, that's not perhaps quite